Hello everybody. Today we'll start lecture 29 and the course is corrosion protection methods, and our discussion point is change in environmental factors and associated corrosion protection. For the last few lectures we have been discussing effect of environmental factors like removal of corrosives, change in concentration of corrosive, addition of oxidizer or removal of oxidizer, as well as we talked about change in partial pressure of oxygen. Those factors we talked about. Now today we will talk about, as well as we talked about temperature, increase in temperature. In most of the cases we see increase in corrosion rate, but in certain cases increase in temperature, initially the corrosion rate is very low, but as we increase the temperature at certain critical value, we can get a very high corrosion rate, and in some instances actually increase in temperature does reduce the corrosion rate. So we have seen those instances and also had some examples, and we tried to understand with reference to mixed potential theory. And please understand that the mixed potential theory is very important to understand many of those corrosion events, and if we understand it correctly, definitely we can devise or we can design corrosion protection. Now today we talk about the effect of velocity. If we see practical examples or a practical uses of metals and alloys under corrosives, some cases definitely the fluids or corrosives are stagnant. At the same time, many cases you would see that the relative motion of fluid and the metal surface would be existent, because in case of pipeline system or cooling water system, all the time the fluid will be moving. Okay, so that case we would have effect of velocity on the corrosion rate of that metal. Okay, and this effect of velocity or the movement of or the rate of movement of the fluid with reference to the metal surface would have varied effects. So at times it cannot have any effect. So with the increase in velocity, the corrosion rate would remain constant, fairly constant, and then there could be a situation that initially the corrosion rate would increase, and once the velocity reaches to a critical value, the corrosion rate decreases to a very low value, and with the increase in velocity further, the corrosion rate remains constant and maintains at a low value. Okay. So again, there are instances like initially the corrosion rate would be very low, and then once the velocity reaches some critical value, the corrosion rate increases enormously, or sometimes exponentially the corrosion rate increases. So we will try to understand those effects with reference to a couple of things like mixed potential theory is one, and then there could be influence due to the formation of some film on top of the metal, which that film forms due to the reaction of that metal with the environment, and the velocity would have effect on those films. So we have to understand that part. Fine. So let us look at the effect of velocity. Now couple of observation already we have understood, like stagnancy or stagnant fluid or electrolyte leads to pitting and crevice. Okay. So that suggests that if we have some sort of turbulence or movement, then definitely these two localized form which are extreme dangerous localized forms of corrosion. So, these can be prevented. Fine. So, it suggests that increase in velocity can be beneficial to the material when we have pitting and crevice kind of corrosion. Okay. We know why, because when we try to look at the mechanism for pitting and crevice, we see that the differential aeration cell forms. Okay. So, what happens? Let us say this is my pit, okay, a small pit. So, there is a small pit that has formed. So, this pit is actually zoomed here. Okay. Now, what happens? Outside surface, so this is my outside surface, we have sufficient dissolved oxygen which will react with H2O if we consider neutral solution and then form 4OH minus. This cathodic reaction would happen, and you could see that entire surface is, apart from that very tiny narrow portion where pit has formed, rest of the surfaces can have this cathodic reaction. So, in order to meet the need for these 4 electron for that cathodic reaction, so we have to have dissolution of the metal inside that pit. So, M minus 2E equal to M2 plus, considering that it is bivalent metal. Okay. It can be written also M minus Ne general form Mn plus, and in this case N is nothing but 2. So, rapid dissolution would happen in this small pit segment. Okay. Now, when this happens, we have excessive metal ion or positive charges. So, we have very large positive charges that are growing. In order to neutralize these positive charges, because the negative charges should come in, if we have chlorine ion, that chlorine ion can come here. If you look back and go to our previous discussion, then you can see that why chlorine ion comes here, because chlorine ion has a higher mobility. So, that is why chlorine ion comes here, and then it reacts with this metal ion and form metal chloride, and this metal chloride later on reacts with H2O, or we call it hydrolysis. So, this hydrolysis product is nothing but MOH whole 2, which is nothing but the rust plus HCl. So, it is basically 2 HCl, where you can write this as H plus Cl minus. Fine. So, now we could see that the hydroxide is forming and which is settling down, but at the same time you have H plus ion, which increases the acidity of that particular small segment. So, it increases acidity, or pH drops down, and once pH drops down, it actually enhances the attack in that zone. Okay. So, further rapid dissolution of metal would happen in that small narrow pit zone. Now, come to velocity or the turbulence. Now, these happens when there is one criteria which is called stagnancy, stagnant fluid. Now, if stagnant fluid is maintained or stagnancy is maintained, this oxygen can only ingress to this particular segment, which is the narrow segment of that pit, by diffusion, and that diffusion at room temperature, if we consider, could be very slow. Now, if we put some stirrer, so that means if we have churning in that particular electrolyte, which is nothing but the aqueous salt solution. So, stirring. So, if we stir, we are actually leading to little bit of relative movement. So, when we have relative movement, that actually takes oxygen from the bulk and it can take it there, okay, because of relative movement. That particular movement would be much faster than the normal migration by diffusion. Okay. So, this allows oxygen to go to the pit, and this actually led to avoid differential aeration shell. Since when pit happens, we could see that oxygen is more on the outer surface of the pit, and inside the pit we do not have oxygen. So, that is what we have difference in oxygen partial pressure or oxygen content. That means that we have a differential aeration, that indicates the differential aeration, and that forms a differential cell. So, you have a positive here and this negative terminal in the galvanic couple, and then current will flow from positive to negative through the conductor or through the metal, and current will flow from the electrolyte through the electrolyte from negative terminal to positive terminal. So, this is the current flow direction. Okay. So, if we do not have this differential aeration cell, then everywhere we have oxygen reduction. So, there will be no oxygen depletion in that small narrow pit region, then we can avoid pitting. Similar situation happens in case of crevice. So, that means a little bit of velocity or the churning helps to avoid differential aeration cell, and that avoids formation of pit or crevice. So, if some material is susceptible to pit and crevice, stagnant fluid or the stagnant aqueous electrolyte is at all not good. Okay. So, this is one protection methods we can think of. So, instead of having stagnant fluid, we can have little churning in that particular medium. Okay. So, this is one part. The second part, we can think of a kind of behavior of corrosion rate with velocity. There could be certain patterns. So, if I try to plot those behavior, let us say this is corrosion rate and let us say this is velocity. Now, depending on whether the corrosion process is activation controlled or concentration controlled, the situation could be different. Now, what do we mean by activation and activation and concentration control? So, there could be two control. One is activation control and second thing is concentration control. So, here it is basically the corrosion control process. So, now what do we mean by activation control? When the corrosion process is via active polarization control. So, if we consider again this E versus log I plot. So, this is the metal dissolution part, which is the anodic part. Let us say this is M minus Ne equal to Mn plus, and let us say we have some oxidant, and that oxidant is actually going to get reduced. So, this is my oxidant plus Ne, it goes to reductant. So, this is oxidant, this is reductant or ox or ret. So, if this process we have the polarization, then it corresponds to IC, and this is corresponding to IA or anodic polarization current density, and the other one is cathodic current corresponding to cathodic polarization current density. So, these are the two segments, and corresponding values you can think of. This is E equilibrium of cathodic reaction, this E equilibrium of anodic reaction, this is I naught metal on metal surface, this is I naught ox on metal surface, right. So, this is my I core or corrosion current density, and this is my E core corresponding to steady corrosion potential. When we have this kind of interaction, you could see that both the polarizations are activation controlled. And the mixed potential, which is this point, is also achieved due to the interaction between two activation controlled polarization, both the cathodic as well as anodic polarization. That time we call it corrosion is controlled by activation process. Now, when we have this, if we increase the velocity, then the change in the process could be in the form of concentration polarization. If we change velocity, the change in this polarization could be in the form of concentration polarization, or concentration polarization can get influenced, okay, when we change the velocity. Why? Because we know that I max, which is the maximum current density that is possible for taking the reduction process at the metal surface so quick that whatever metal ion or the oxidant comes to the metal surface, that get immediately reduced. So, the concentration at the metal interface, metal liquid interface or the metal electrolyte interface would be almost 0, and the concentration away from that metal interface would be, if you consider the bulk concentration of that oxidant or the reacting species ion, would have a value of, let us say, the bulk concentration. So, when it happens, what I mean to say that, let us say if I try to look at the metal surface, and in the beginning we have some concentration, let us say this is C naught, which is the concentration of that reacting species, let us say oxidant concentration, we call it ox, and this is metal surface. Now, the metal ion or that oxidant reacts with electron and then form reductant or red. So, then if the rate of reaction at the interface, this reaction rate is not that fast. So, then the process will be controlled by activated jump of that oxidant over the activation barrier from the fluid side or the electrolyte side to the metal surface. In fact, whenever a metal or electrode is there, there would be double layer. The inner double layer, IP, we call it Helmholtz double layer, or plane, and this is outer plane. So, now what happens if the rate of reduction process, here we consider a reduction, if that rate is slow enough, then it will be decided by the jump of that ion from the metal surface ox red. So, we can take it as hydrogen ion and this is going to hydrogen. So, this is my activation barrier. Okay. So, that way the process will be controlled. Okay. So, if you want to understand this, again I would request you to go back and then see the previous lecture series where this is clearly explained. Now, this activation jump, when it happens, that time the typical graph what we see for the polarization is like this. So, here what we have shown that there is a straight line in the log scale, on the current axis, and potential axis on the y axis is on the y axis, then we always see these straight lines. But if this during this reduction process, the reduction rate is very fast, then definitely there could be depletion of this concentration, oxidant concentration at the outer Helmholtz plane. So, once this particular outer Helmholtz plane gets depleted with this hydrogen ion, which is here as an example we have taken as oxidant, then the process will be controlled by the diffusion of hydrogen ion or the oxidant from the bulk to the outer interface. Okay. So, that time we will get a kind of distribution. So, this is my, let us say, the this concentration of oxidant, and then there could be diffusion barrier, and then we will have a small diffusion layer which is delta, and that way we get, or the boundary layer we call it delta, and then the diffusion path, if we consider the steady state diffusion, so this will be my pattern of the concentration profile. Now, this particular interface, that as the rate of reduction increases, this point gradually will go down. So, that means the metal ion, or sorry, that hydrogen ion or oxidant species which is coming to the interface, which is outer Helmholtz interface, when it comes there, the rate is so fast, immediately that would get reduced. Fine. So, because of that, at certain point it will, and when we have this, that time gradually the current density corresponding to the cathodic rate process would gradually go up, and at some point of time we could see that the current density would reach maximum, and that point whatever oxidant species would come to this particular interface, it will get reduced immediately. So, that means literally the value corresponding to that limiting value, the concentration value, if you see concentration value would be 0. Okay. So, that point will achieve I max, which is the maximum current density corresponding to the reduction process. Now, that I max relates to few things. One is number of electrons for the reduction process. Here it is considered as N. If we consider hydrogen, then H plus ion will be getting reduced. So, there N will be 1. Then we have F, which is the degree, which is the Faraday's constant 96500 coulomb per 1 mole of electron. Then we have diffusivity, then C naught divided by delta, which is the diffusion distance or the boundary layer distance. Now, this particular I max is the maximum current density that is possible, and once that maximum current density is arrived at, that means whatever species that is coming, or the oxidant that is coming at the surface of outer Helmholtz plane, that would immediately get oxidized, immediately get reduced, and then the concentration at the interface of that oxidant would be 0. So, then we will get I max, and when I max is achieved, so then my voltage would be infinite, okay, because over voltage is written as so this is the over voltage equation, and these over voltage we are considering, since we are considering concentration effect. So, we call it concentration over voltage, and since we are considering cathodic reaction, that means the reduction process, we can also call it cathodic. So, now when the system or the corrosion process is controlled by cathodic polarization, we mean to say that the interaction of the anodic part of the metal, that means the dissolution of metal part with the reduction process on E versus log I plot, it is also talking about mixed potential. So, that time the system would be considered as concentration controlled corrosion process. So, this is E volt log I ampere per centimeter square. Now, if I try to plot this for the cathodic process, initially it will be activation part, and then we get concentration polarization. So, this is nothing but I max. Okay. So, this will be typical plot. Now, how the interaction of the metal dissolution part or the metal dissolution anodic polarization part is taking place, that will decide whether it is a concentration control or activation control. So, now if the metal dissolution line or the polarization line is interacting in the active part of the reduction polarization line. So, this is reduction polarization and this is oxidation polarization. So, interaction could happen like this. So, that time this would be my I core and this would be my E core, but if the interaction happens here, okay, so then this is same as oxidation process. Now, the reduction process has reached the limiting current density. So, it is at this location, this will be my I core and this particular point would be E core. So, this is concentration controlled and this is activation controlled. Now, if the corrosion process is controlled by the way interaction happens at this location, then it will be concentration control, and if the corrosion process happens because of the interaction of the activation polarization part, then it will be activation control. So, these are the differences, basic differences. Now, if we have such kind of situations what we have seen here, okay, then there could be serious effect of concentration, serious effect of the velocity of the electrolyte on the corrosion rate of the metal. Now, if we change the velocity, what could have changed? Now, I know that this is my relation which is I max. Now, if we increase velocity, velocity is increased, then I can increase delta could be reduced. Okay. So, delta, why delta could be reduced? Because this boundary layer, the diffusion layer, that will shrink because of the increase in velocity. If that shrinks, then this should go up. Okay. So, we could see that if delta decreases, I could have higher I max. So, the curve will change to this location. Okay. Now, if we further increase the velocity, I max will further increase. So, it will be here. If we change the velocity further, so it could be here like that, and then it could be here, all those velocities. So, I could see that I max is increasing, I max increases, velocity increases because delta or the boundary layer thickness decreasing. So, now when it happens like that, if we try to plot the corrosion rate in these two processes, process 1 and process 2, this is let us say 1, this is 2, what will be the corrosion rate variation? So, in case of process 1, let me just draw it here. So, we can plot it here. This is velocity. If it is activation controlled, I could see all the time the corrosion potential as well as I curve, they remain at the same point. So, if we try to find out the corrosion rate, it will be a flat line with respect to velocity. Now, if we have a situation the way it has been shown in case of case 2, we can have situation like this. The corrosion rate, you could see that initially it was here, then it goes increasing, this increasing, and then once it crosses this is the point which is very crucial. After that, increase in velocity would not have any effect, because that time the anodic part for the metal dissolution is not actually cutting the cathodic part in the concentration polarization part, rather it is cutting in the activation polarization part, and then the corrosion rate again would become a constant. So, the corrosion rate pattern would be like this. We are just drawing a schematic plot. So, initially, so that means if I try to see, if we try to give point different marking, so this is let us say 1, this is 2, this is 3, this is 4. So, once it reaches 4, so this should be velocity 4, this is velocity 3, velocity 2, and then this starting point, let us say this is velocity 1. So, with the increase in velocity, we gradually increase the corrosion rate because of this typical interaction, and that is shown in the mixed potential plot, and then further increase the corrosion rate remains constant, this constant corrosion rate. So, this two behavior we can notice. Example, let us say case 1. So, this is the case 1, it can be shown by iron in dilute HCl, and there we have interaction like this. So, this is hydrogen evolution, H plus E equal to H, this is iron dissolution, okay, and this is my I core and this is my E core, typical plot of this nature, case 1 nature, fine. This kind of in case of case 1, the interaction happens in the activation, the interaction point would be guided by interaction between two activation polarization line. Now, case 2, can happen in case of iron in water with a little amount of dissolved oxygen, very little amount of dissolved oxygen, then this particular behavior can be noticed, or copper in H2O plus O2. So, this O2 which is the dissolved oxygen is a little amount. Okay. So, then this behavior can be noticed, where the interaction would be between the activation controlled anodic dissolution and concentration controlled cathodic process. So, then we can get such behavior, which is case 2, this is case 1. Right. Now, there could be a change in this particular case 2 pattern if we have active passive material. Okay. So, if we have active passive material, and that time let us see how the interaction happens. This is E volt log I ampere per centimeter square. Now, let us draw one active passive metal. This is my active passive metal. Now, let us say this is E equilibrium of metal dissolution, this is I naught on metal surface, and let us say some oxidation process is taking place like this. Let us say it is here. So, this particular plot if we consider six velocity of that particular fluid, where we see the interaction between active passive metal with the cathodic polarization line consisting of activation part and concentration part. So, here for example, in this particular case, the first case, so up to this part we have activation polarization, and from this onwards we have concentration polarization. It is same as what we have seen in this situation. Okay. Now, if we start with a bare metal without any passive layer, then we know that the metal dissolution process or the anodic polarization as well as cathodic polarization, they will try to take the potential to a certain value between the extreme potential, which is equilibrium potential. Here the equilibrium potential is of the oxidant. So, here this is oxidant plus E, let us say reductant, this is the reduction process. So, they will try to reach to a in between potential where the rate of cathodic reaction is equal to the rate of anodic reaction. Okay. So, now initially this was bare metal, no oxidizing, no oxides or no passive layer. So, this metal polarization would start happening along this line, and cathodic polarization line would start happening along this line initially, okay, when the velocity was v1. Now, then we could see there are three interaction points. One interaction point is at this location, then at this location, and then at this location. So, now all those three locations you could see that the total rate of anodic reaction is equal to cathodic reaction rate, because this indicates IC, this indicates IA, and all those points I could see that IA equal to IC if we look at the magnitude of it. Okay. But since the metal is bare, when we dip that metal in that particular electrolyte, the system will maintain the first interaction point, okay, which is the interaction at the active dissolution portion of that active passive metal. Then if we keep increasing the velocity, we will keep getting 3 interaction points. Here also we are seeing 3 interaction points. This point is common, these two. Still we increase velocity, we are getting 2 interaction, this is 2 interaction, and then this is one interesting point where we have 2 interaction. One interaction is at I critical, which is the maximum current in with this particular current drawing. This is the maximum, this point is I critical, okay, I crit. You please go back to the previous lecture, you can get to know what is I critical. So, there again, since this is the interaction point, which is the maximum current density in this current plot pattern. So, it will have a very high dissolution, and this is also considered to be interaction between active polarization of the anodic process and concentration polarization of the cathodic process. And then the system will try to maintain the corrosion rate at this location. Okay. Now, see, if we increase the velocity little more, then the point is actually moving beyond I critical. This particular cathodic polarization line is bypassing I critical, and this bypassing is very important for active passive metal. So, once we bypass this I critical, then we could see that the only one interaction point we could notice, that is this particular point, and this green point corresponds to, or let us say I put it in this color, brown color. So, this particular point corresponds to when cathodic polarization bypass I critical, and then the system will immediately take the interaction between two reactions, cathodic and anodic reactions, will take the potential or the mixed potential to this location, which will be considered as E core, fine, and the corrosion current density would be equal to IP or the I passive. And you could see that because of this bypassing, the corrosion, this particular metal approaches passivity and will go to a passive state. And once it goes to passive state, the corrosion current density would be as low as IP or the passive current density, and it will maintain that particular current density with further increase in velocity. Okay. So, that is the beauty of it. In certain metal and certain environment, this particular process happens, and then the corrosion rate pattern with the increase in velocity would take this form. So, the 6 velocities we have considered. and if we can go further, the velocity is actually increasing. Now, as we see those interactions, so this will be my first I core 1 corresponding to I max V 1, then it will be I core 2 corresponding to I max V 2, like that it will progress, and then I will get initially the corrosion rate would go up like this to V 5, and then the corrosion rate would immediately reach to I p, and then that particular corrosion rate will be maintained and the material will passivate. So, the corrosion rate pattern would be, it will go like this, then it will go down to a very low value and there it will maintain. Okay. So, now you see initially corrosion rate increases and then this is corresponds to I p, and here with the velocity the material is actually maintaining active dissolution, and once that V 5, which is the critical velocity just touching the I critical, once we cross that velocity from V 6 onwards, we get V 5 onwards rather, we get a strong passivity and material would maintain a low corrosion rate, or we can say that we can achieve very good corrosion protection. And this particular thing we call it as case, let us say case 3. So, this can be achieved in case of 18-8 stainless steel in H2SO4 plus Fe3 plus. So, this is sulfuric acid with the presence of a strong oxidant which is Fe3 plus. So, there we can have this kind of behavior. So, this is related to the velocity and its their explanation with reference to concentration and activation control corrosion processes. So, there could be one more situation where if I try to plot the corrosion rate versus velocity, so there initially the corrosion rate would maintain a plateau with the increase in velocity, and once we reach a critical velocity, let us say this is V critical, corrosion rate will increase at times exponentially. This case could be considered as case 4. So, this 4 can be this behavior can be observed in case of lead in H2SO4 or dilute H2SO4. Okay. So, initially this lead gives you at a low velocity forms lead sulphate on top of it, which actually protects the material from corrosion, but as the velocity is increased, there could be possibility that the layer which protects that lead can get dislodged due to the erosion effect, and that once it gets dislodged at a higher velocity, and if that velocity is maintained, it will not be able to reform, and when the reformation is not there, the lead would dissolve at a very high rate. That is what exactly happens here. So, this is the problem what we can experience in case of lead in H2SO4. So, in case of lead in H2SO4, of course, it has to be dilute. If H2SO4 is concentrated, the situation would be different, because if lead in H2SO4 concentrated, then again the pattern would be similar like this. We have explained that the change in concentration of corrosive. But if we consider this in the dilute medium, if it is a stagnant, then lead gives you a fantastic protection, because it forms lead sulphate, but at a higher velocity lead sulphate will be dislodged, and then it will have exposure of the lead surface to the acid, and then it will keep dissolving at a very high rate. That is what we experience this curve. So, you could see that a strong experimental understanding of the corrosion of metals and alloys in different environments is very much needed. Otherwise, we will not be able to understand how to protect that material. So, this is in brief, we try to understand a lot of aspects of corrosion protection or corrosion behavior with the change in environmental factors. So, we'll finish this today, we conclude this today. From tomorrow onwards or from next class onwards, we will try to look at the effect of inhibitors as well as coating. And then later we will also talk about effect of change in potential of metals and alloys in an electrolyte for getting protection. Thank you, and we'll discuss further in our next lecture. Thank you.